Good morning, everyone. Welcome to the EasyPower Tuesday Refresher Series. My name is Jim Chastain. I'm an applications engineer here with EasyPower. I apologize for the name of the session. It seems a little bit, I don't want to say lame. It doesn't really emphasize where I wanted to go with the discussion. And you'll see as we get into it that the emphasis is on how to get more value out of a one-line diagram that was required for short circuit analysis or arc flash. So we'll get into that detail as we get into this. Appreciate everyone attending today. As we are in the habit of doing, wanted to run a couple poll questions by you just to get some feedback. No obligation or liability, but would appreciate your responding in kind. First question, how frequently do you or your clients require load flow or power flow analysis? And again, there's no right or wrong answer. It's just an estimate, and you'll kind of see where we're going with this as we get into it. And part of this is understanding the value of what load flow does. So it looks like we have a quorum here. All right, let's close this out. See how folks have weighed in on it. All right, so that's pretty much as I expected. The next question is, do you or your clients have SCADA data monitoring equipment on their electrical system? And again, this is something that's becoming more and more prevalent, and it makes the task at hand as far as tracking load flow much easier. And I'll amplify. So you might say, well, why would someone be doing load flow more frequently than once a week? Case in point would be if I have to do some maintenance and some large portion of my system or any portion of my system is going to be offline. What does that do to the rest of the system? Do I need to shift loads? Do I need to balance out the remaining part? And that answer comes from a load flow analysis. So here's how folks have weighed in on this question. Looks like we have over 50% on the critical elements with SCADA data. Thank you. And then finally, do you know if any of your clients use that SCADA software to automatically run a PowerFlow? And this, I don't have a clue as far as how widely spread this is, but that's why I included the question. There was a day, especially before arc flash became so prominent in the safety arena, that PowerFlow was pretty much the focus of most engineering groups or facility engineers. So here's how folks have weighed in on this one. Good. Well, thank you for participating. That helps a lot. And while there's no real surprises, it's interesting to get to see where things are kind of shaping up there. So let me jump into what I wanted to talk about. It sounds like someone may be having audio problems. Looks like let me double check the settings. Is anyone else not hearing me? Just a second. Nope, we should be in good shape. Okay, sorry about that. Just one person's having a problem. All right. So the objectives today is to talk a little bit about what load flow is, not making an exhaustive examination or even an exhaustive demonstration. I do want to emphasize how to modify the digital model, which is a one-line diagram that was used for arc flash, because there's a lot of value that can be extracted from that with relatively little additional effort. And then talk about a couple of typical examples. Now, load flow or power flow is essentially the first thing you run into in a power systems collegiate class. And the application may not be amplified as much as the calculation part, but in the age of computers and the level of software that's available, we don't use slide rules anymore. In fact, we don't even do hand calculations that often. And so some of the dependence or focus on load flow has kind of fallen by the wayside. So one thing to point out is that it's a calculation, a snapshot in time for a given load, supply, and network condition. And part of the restriction is that there has to be at least one swing bus which has the ability to supply or sink real and reactive power for a given voltage. Now, there could be other generators, there could be other swing buses as far as that goes. But for the most part, at least in EasyPower, you need to at least have one. The basic power flow problem is circular in nature. And that is, the power drawn by the loads varies with the voltage. But then the voltage will vary with the current that's drawn by the load. And so they're interdependent. And for any given condition of load and supply, there can be the ability to solve the resulting equations with an iterative process. And in this case, computers are very good at this type of calculation. Voltage drop is simplified by the fact that we're requiring constant loads. And again, the snapshots, so the loads aren't necessarily changing. And in the tools, you'll see we calculate a quiescent point based upon the static loading that we've indicated. The PowerFlow solutions is based on the complete, in other words, the voltage and available current at any given bus is dependent upon the voltage on every other bus in the system. And so there's not such a thing as doing a single bus solution. You have to do the whole system to get any results that are accurate. Now, this is always something that's a little bit difficult to envision if you haven't bought into the process. And that is, we're talking about the difference between real power and reactive power. And the real power is what we get work, what we use to do work. And the reactive power is what it takes to overcome the impedance, the reactive impedance of the system. And so the result, which is calculated by doing the square and the sum of the other two components, is called apparent power. And you got old Pythagorean theory that gives us the results. And so part of the goal is to understand where we're getting the real results or the real work done versus impediments that the system may present. Now, when it comes to computer analysis of these types of problems, there are three widely accepted power flow calculation methods: the Newton-Raphson fast decoupled method and the current injection method. EasyPower uses a current injection, which is a derivative or takeoff on Newton-Raphson, and employs the sparse matrix solver. Essentially, we do a matrix of what we call the admittance matrix. And admittance is the inverse of impedance. What that gives us is a sparse matrix that allows much quicker calculation, and the result is more robust than the Gauss-Seidel method. All of that means nothing until you start trying to analyze a large system, and the net result is you'll get a faster result using the EasyPower methodology. So the way this is set up is you assign a voltage and a power angle at each bus. Usually it's a per unit of 1, and then you go through the matrix calculation and determine what the errors are between the incoming power and the outgoing power. You increment the voltages on each bus and you do that calculation again. So the idea is to minimize the errors and converge on a point in that solution that you basically get the incoming power equals the outgoing power plus the load loss, plus the loss of at that particular bus. Now it's important, now we're going to start with a one-line diagram that we used for short circuit analysis. And if you'll notice, and you'll see this as we get into the example, when we were setting up motor loads and even linear loads, we would set it up on the pretty much on the basis of 100% operations, 100% load. And in the real world, that may not be the case. So what we need to do is tune that one-line diagram content or loading profile to match what our actual system is. And so there's several sources of data that can be used to refine that the model. For starters, the utility company is very good at delivering data on real and reactive power flow at the point of connection. And so to refine the your one line as a first order approximation is to make sure you're having loads that line up and give us utility interconnect that the utility company has determined for us. Now, if you have metering data, that's even better. You can refine down to the bus. And aside from that, you can make some assumption based upon the speeds or load that you're putting on the individual motors. And this can be done in mass to give us a first order approximation. We'll get into that in the example. Now you might say, well, what's the difference between PowerFlow and the NEC calculations that we took on when we designed the system? Well, NEC specifies how to compute loads for equipment sizing, and basically you just total up the total loads per the NEC rules, and that gives you a estimate of what the total capacity of individual elements needs to be. Generally, they're very conservative. So you'll see utility companies put in transformer substations that are sometimes 50% of what the total load calculations were, or estimate was determined to be based upon the type of industry that the utility is serving. But the NEC loads determine breaker size, feeder size, and short circuit calculations. PowerFlow is generally based on actual loads, and that's why there may be a difference between some of these guides that you have available to you. And as I mentioned, there's different sources for this information: the billing data, power quality meters on the equipment, ammeters on panels and motor control centers, and most SCADA systems that have the ability to export the data. All this will give you more accurate representations of what the load at any given time. And at that point, it's up to you to kind of data log, if you will, the time that you're going to do the PowerFlow analysis. EasyPower allows us to scale loads to align with the results that we've indicated, and then modify our one line to, if you will, take up the slack. If there's loads that aren't being recognized by our one line, we'd have to make sure that was included in the one line, because there could be loads that we didn't include because they're not short circuit contributors during a fault. Now, if no other data is available, you can scale the connected loads based upon an estimate of what their running capacity is or is used, and or the transformer rating that the system's set up for. But based on these estimated data, you can run a worst and best case scenario for your load PowerFlow calculations. PowerFlow studies can be used for equipment sizing, generator voltage and governor settings, loss evaluation, and trend analysis, and predicting issues with equipment. You might say, well, I do that with thermography now. One of the issues with thermography is if you're not taking the image at the maximum load that the equipment's designed for or usually runs at, you may not get an image that indicates there's a problem, whereas load trending or loss trending that you could track in PowerFlow at least would give you an idea when to take the snapshot of the thermal image. In industrial facilities, as I mentioned, plant load changes is a good application for load flow, power factor correction, tap settings, cogeneration, plant expansion, and predictions on issues. We're talking about plant outage. Now, I don't have time to run through an example for each of these, and so I'm going to focus on basically taking a one-line diagram and walking through a couple of these examples. So let's start with transformer tap settings. So when we set up a transformer in EasyPower, first of all, I wanted to talk about the motors. When we set up a motor load in EasyPower, normally in our PowerFlow settings, it's by default set up for 100% load, and we usually don't, because in an initial design, we don't know what the anticipated run rate's going to be. So for the most part, most one-line diagrams have load set up at 100%. Secondarily, when we set up a transformer, we set up the taps to be equivalent to the incoming or the incoming and outgoing voltage buses that we expect to be running. And that may or may not be the case when we're in actual production using the typical loads. So if we go into PowerFlow right now, again, I'm using the one-line diagram that we used for short circuit analysis. This isn't a design demonstration. This is strictly illustrating how to use the tool for this particular function. I'm in PowerFlow. I'm going to go and solve the equations, and what we see is a bunch of numbers. If you look at the top row up here, I have the ability to turn on and off the voltage at each bus. And what we see is the voltage, this is 13.8 K bus, and we see during this particular operation, it's running at 13.46 with a power angle of negative 2.2. Good, bad, or indifferent, we can talk about that. I can also show the loading on the motor load, turn it on and off. We can show the branch flow. What we're showing here in both the to and the from each bus is above the line is the real power. If I go into my PowerFlow options, I can see what the units are on my one-line output. For branch flow, I'm looking at megawatts and megavars. So this particular branch is supplying 1.383 megawatts and is being pushed along by 0.856 megavar of reactive power. Then my generator and load are going to show MVA and power factor, and the losses will be in kilowatts and kilovars. Right, if I want to amplify or turn off the loads, I can do that. Branch flow, we talked about. Transformer taps. Now we're showing the transformer was tapped as the same way it was set up, but is that the optimum setting for our steady state operation? Well, again, once we've decided the load and the capacity of the plant, we know that this particular bank of motors is going to be running at 88%. So let's go ahead and scale the motors to 88%. That will change some of the design. And secondly, let's optimize the tap settings for the transformer. Well, to do this, We're going to go back to our database edit, save our changes that we've made short term. And in the setup for the transformer, there's a tab called LTC, or Load Tap Changer. Well, the transformer doesn't have an automatic one, but we're going to use its capabilities to optimize in PowerFlow the effects of a load tap changer. And so if we set to adjust the from side, the 13.8 kV side, we can change the tap there to hold the output voltage to the 1.0 value, or the 480 volts. The tool will optimize using those capabilities in the load tap changer. So now we go back to PowerFlow, solve the equations. And if I look at my load tap now, I'm showing if I tap this at 13.21 kilovolts, I could hold my output at 480 volts with this loading. So what I want to do at that point is go back and change my tap on the transformer to 13.21. So let's go back and do that. Take off the load tap changer, set up my tap at 13.21. And now whenever I run my PowerFlow and solve, I get the correct voltage out of my transformer. So that's how you do a load tap changer. The next thing we wanted to do is power factor correction. So let's close this puppy out. So power factor correction, especially in an operation similar to this, is a big deal because we have a lot of motor loads, and it's important to know what the effect on power factor is in general. So we got the same one line without doing the load tap. I'm going to go ahead and go into PowerFlow. Let's leave everything at 100% loading for now. Solve PowerFlow. And if we go up and look, if you remember, this is MVA and power factor. We see our power factor at the point of connection, or the utility interface, to be 0.843. Well, in the Northwest, this would invoke, under most conditions, most utility companies, a substantial power factor penalty, power factor demand penalty, that would encourage us to do power factor correction. Well, most of this power factor loading is due to the reactive power that has to be pushed along with the real power. In this case, we see a total of 4.88 megavar has to be supplied to get the real power delivery of 7.66. Well, knowing what our one-line diagram contains, we have some large 3,000 horsepower motors here, and this is probably the biggest source of that power factor, of the reactive power demand. So the question is, what can we do to mitigate? And so what's wrong with having this much reactive power? Well, first of all, it's producing some amount of loss at every intersection with the transformer, with the cable, and even in some cases with breakers. So power factor correction on this bus seems to be a good idea. Well, if we look at this in 100% power, well, let's say now that we recognize this, we know these motors are running at, let's say, 92%. So let's set this scaling to 92%. And that shows that we have a 2.307 reactive power demand at this point. So we need to compensate for 2.307 megavar. If I go back to database edit, now this, I'm not designing a power factor correction, I'm doing a what if. What if we did power factor correction by putting in a capacitor bank on that motor bus? Let's put in a switch just so we can see what happens. And now we were talking about a 2.5 megavar value, so let's put in 2.5 and see what that does to my power factor correction. So go into PowerFlow. I'm going to open the bus just to make sure we didn't change anything and solve. All right, we have a 2.3, so I missed it by a little bit. So if we close this and put this capacitor in line, now you can see I've overshot it because we're supplying reactive power out, so I need to adjust that. But it brings down my reactive power flow through this feeder substantially. And you might ask, well, where does that current go? Where does that reactive current go? Now it circulates or recirculates between the capacitor and the motors at the rate of 2.43 megavar. Now, what did I do to our power flow with the utility? It brought the power factor up to 0.96 and eliminates the power factor demand penalty to the rate of $10,000 a month in some cases if we have this on full time. Now, there are a lot of other things to be considered, and I'm not going to go into the details of it, but let's just say, well, what are the other choices for reducing this power factor demand? Well, I've heard that VFDs can be a good source because they reduce the power factor as well as the real power in some cases. Can we get this much reduction in power factor by using VFDs? Well, let's try it out. Let's go back to our database edit. Let's take this capacitor out of the circuit. I'm just going to deactivate it. And let's change these two motors to a VFD. So I'm going to open up the motor, make it a VFD. So this won't change the short circuit on a non-regen because it doesn't supply, well, it will change it because it doesn't supply any short circuit current during a fault on the bus, but it's mainly going to be affecting the power flow. So we're going to leave it at 92% run rate or capacity. Now we have VFD drives here. We want to see what happened to our power factor or our reactive power. Now we can see we've reduced it from 2.5 down to 0.88, so it's a substantial reduction. And our real power that's being drawn by the motors has changed, and I'd have to go back and check it. But now my power factor to the utility has also improved considerably. And so the question is, what's the cost of doing a VFD conversion versus doing power factor? Again, there's other ramifications. The first of which is, well, depending upon what frequencies that this VFD control will put on the system, I probably need to have some sort of filtering, which is going to impact the cost. And that's something else we need to do. So anyway, we've identified two different ways to eliminate the power factor correction issue with the point of coupling with the utility. And again, it took us all of 5 minutes to say, what if we did such and such? Obviously, to get into the details of this, I want more data on the other motors involved and the resonance of my system. Okay, then I want to talk about estimating losses. So let's kind of jump back into this and see what's going there. If we look over here at this particular bus, we have this on an ATS, so presumably it's the emergency systems. And while it doesn't have any motor loads because there's no reactive power going on, is it going to be equally capable if we switch over to the standby generator? So as I do that, I notice I have, and what I'm looking at is overloads here. And that apparently, if I look at the units, I have a 25 amp rating on the cable, and I'm demanding 185 amps when we're in on the generator. So what's this an indication of? Well, it could be I had a problem with my arc flash one line to start with. I either miscollected the data, which is another reason to suggest you can use PowerFlow to do a data check on the information you've collected for the one-line diagram. And if you end up with a situation like this, could it be that I had multiple conductors that I didn't take into account, or did I just have a missizing situation? But in any case, if this is real, then I have a real issue when I'm on emergency standby power. So but the point that I'm trying to make is this gives me the ability to check on scenarios that wouldn't be normal concerns doing an arc flash study. So I look like I have this set up for a number 12, which again is rated for 25 amps. So clearly I made a mistake, and I need to go back and check my notes. But for some reason, I need to have either a larger diameter wire or multiple conductors going to the generator. So by changing it, if I go back to my PowerFlow and solve, I can see that I'm still, I need to go up another notch because I'm still within 10% of the rating at the 100% load. So maybe that's the other thing. If I say, well, normally this will be at 85%, is that going to be adequate to survive? And the answer is yes. It's only going to be 128 amp draw on normal operations. Okay, so what am I trying to do? Just trying to show some applications. One, how easy it is, relatively easy it is, to take a snapshot of the impact of changing loads in my system, of trying to mitigate power flow correction, of verifying that my one-line diagram is correct in terms of the ampacity and the loads that we've connected, because the original design may have been set up without accurate data on the loads. So among other things, PowerFlow can be used for transformer load tap sizing, power factor correction, tracking changes in losses or impact on capacity if I'm going to be able to de-energize or move equipment around. And above all, it gives us the ability in very short order to go through what-if scenarios to answer some initial questions or give us some direction on how to deal with changes in the topology. I think that's what we wanted to cover for today. I'd encourage you all to check EasyPower.com for the monthly Arc Flash workshop. I think we still have some openings for next month, or this month now that it's March. We do have live online regional training coming up, and then dozens of technical videos that you can search on topic titles. So thank you for attending today, and we look forward to seeing you down the road. Have a good day.